Right. Thanks, Jim. Everyone can hear me? Yeah. Can I get a thumbs up from
Yep.
someone? Yeah. Okay, great. We have a few minutes before we're formally supposed to start. So in this small amount of time, I'll just remind everyone that our talks are 10 minutes long. So that's typically 8 minutes with time for maybe one question. We're going to stick to the same format that we have in previous years. So any more questions past that time, we'll refer to GatherTown, and hopefully in GatherTown, we'll see that you can walk around and have hallway conversations similar to the kinds of conversations that we had in our in-person events. Anything else I should note? I will cut you off, speakers, if you're over 10 minutes, because there are other speakers and they deserve to have their time slot as well. So I will be very aggressive in that sense. And I was thinking about doing a little like beep at 8 minutes, just to help speakers make sure they're on time. So I'll probably try and do that as well. I'll come in, unmute myself, and say beep, and then very quickly remute myself. Anything else I should add? I think that should be it for our first session. Do we have our first speaker? Are they ready to go? Ariah, are you ready to go? Are you on the line?
Yep, I'm ready to go.
Wonderful. My clock is saying 7:08:55, but we can also start early if you're feeling ready.
I'm fine with that.
Okay.
Let's see.
Try and make sure we can at least share screen. Yeah.
Yep.
Great. Would you find the beep at 8 minutes helpful?
Yeah, sure.
Okay, great. Then I will beep myself at 8 minutes.
Okay, then let me start here. So I'm Ariah Klages-Mundt. I'm going to tell you about our paper Stablecoins 2.0, Economic Foundations and Risk-Based Models. And this is joint work with Dominic Hartz and Louis Gudgeon at Imperial, and Junyo Liu and Andrea Minka at Cornell. So broadly, the last year can be thought of as a year of DeFi, with total locked value growing roughly 20x or even more now, and with systems becoming much larger and much more interconnected. But as a side effect, this also means it's been a year of DeFi crises. And I'll illustrate just a few examples of these as related to stablecoins that kind of motivates our work toward how do you design these systems better. So one example is the Black Thursday event in MakerDAO back in March. We also had a minor attack event on a stablecoin called PegNet back in April. And the DeFi lender BZX had many attacks throughout the year. And just last month, we had Origin Dollar that was attacked and the value crashed to a small fraction of the target. And so this motivates us into thinking about how do you design these systems better, as right now they're kind of designed very ad hoc. And so let's kind of start from the top there. A stablecoin is a cryptocurrency that also has like an added economic structure that aims to stabilize the trading price. And while we have a lot of designs for these right now, they lack sort of risk-based models that span the design space and the trade-offs involved when you're making the design. And so this is a gap that this paper tries to fill, trying to make essentially like a manual that future stablecoin research could use as a baseline for continuing research. And so broadly, we have three parts to this. One is a decomposition of the design space and sort of filling in where traditional financial models can help us understand what's going on. Two is a formulation of fundamental design questions around the design of non-custodial stablecoins. And three is how do we start to make new models to help us understand these non-custodial stablecoin questions. And so let's start with a little flavor of the decomposition of the design space. So I'll walk you through a little overview here, but this is also kind of simplified, as you'll see in one of the later slides. So at a top level, we can think of two types of stablecoins. One is a custodial stablecoin like Tether, another is a non-custodial stablecoin like Dai. And in the custodial stablecoins, we have sort of counterparty credit risk, censorship risks, and traditional financial risks. And luckily, these are well understood. And in the non-custodial side, we have sort of new risks and attacks that are possible, including sort of deleveraging risks that come about from the shape of some of this market microstructure in crypto markets, price feed and governance risk, minor extractable value risks, and smart contract bugs. And these are not very well understood. Now you can take the custodial side, which luckily was well understood, and sort of segregate it into multiple different types of custodial stablecoins and interpret these using existing models like ETF models, bank run models, and sort of pegged money market fund models and currency models. I'll leave the rest of the details there to sort of to the paper because this is a very brief talk. And then sort of focus more on the non-custodial side. So the non-custodial side is essentially sort of designing risk transfer mechanisms. And so let's motivate that a little bit here. So a collateralized debt obligation is essentially like you have a portfolio of underlying assets, and you split this into two tranches. One is a junior tranche that's supposed to be more risky. One is a senior tranche that's supposed to be less risky. And say that you have a loss that's incurred. This is first borne by the junior tranche that is then protecting the senior tranche value. And so a non-custodial stablecoin kind of resembles this, where you have sort of a risk absorption measure that's kind of taking the place of this junior tranche, and then stablecoin holders are like the senior tranche. And then you have also this like added deleveraging process that if there are big losses that are incurred, it dynamically resizes the CDO so that you have something that tries to be like a perpetual instrument that can continue functioning from that point. And this added structure adds actually these deleveraging risks that are essentially like market feedback risks in the activation of these deleveraging processes. And so sort of with this in mind, we can think of non-custodial stablecoins along different types of collateral, one being exogenous collateral, which would be like Ether and Maker, which has these deleveraging risks, endogenous collateral, which would be like SNX and Synthetics, which actually has amplified sort of versions of these risks. And then implicit collateral, which would be kind of like basis, where you have sort of like incentives to try to absorb these risks, but not necessarily forward obligations. And this is kind of where we're going to be focusing for the rest of the overview here. Now, it turns out this is like, as I was alluding to, kind of simplified, and there's like a wider anatomy of non-custodial stablecoin parts and how they connect. There's more details of this in the paper, but sort of very quickly, there's sort of like this primary value idea, which is this different types of collateral. There's a risk absorption process, which is essentially saying who's absorbing the risk and how is it being absorbed. This connects with an issuance process, which is essentially saying how do we determine the size of the stablecoin supply to try to keep the price in line across markets. And then price feeds and governance, which change parameters over time, and miners sort of in the background that can reorder transactions and possibly extract value. And one thing we can do with these sort of multiple dimensions that we have now is visualize the existing stablecoins along those dimensions. And you can check out the papers for some more discussion of that. So that brings us then to sort of fundamental design questions around stablecoins. And it turns out that we need sort of new models to try to do this. And so we formulate two of these questions. One is around sort of incentive security, which is essentially saying, are there mutually profitable continued participation across all of the required parties that were in this previous anatomy? And then supposing that there are, the next question is economic stability. Essentially, do the incentives that you set up, given that there's participation, actually lead to stable outcomes in the stablecoin markets? And as I was saying, we need actually new models to try to address this for reasons that we kind of build out in the paper. And so we construct three classes of models that will hopefully be helpful toward evaluating these going forward. And I'll give you just a very brief taste of these. So one is capital structure models. And these are essentially one period incentive models where we're modeling participation and attacks in these systems. And it's essentially reformulating models for IPOs and adding in new attack vectors. And you can think of it like you're interpreting stablecoin holders as bond holders, stablecoin governance as an equity sort of class, and vaults or like risk absorbers as essentially managers in these systems, because they're actually deciding the stablecoin supply decision in a lot of these systems at least. But you can consider different versions of these to address different types of systems. And this leads to sort of like a price of anarchy that you can find in aligning incentives in these systems. And we actually formulate a conjecture here that if you really want sort of very fully decentralized systems that also have very flexible governance processes and oracles, that there may in fact not be a long-term participation equilibrium under realistic parameters. And this is an analogy would be like there's a bank where you have an it's unsecure if the equity is less than 2 times assets under management, because essentially no depositors will want to participate. We also have forking models, and I'll leave sort of the discussion of these to the papers. And we also have price dynamic models, where we're trying to understand the dynamics of the price process that these stablecoins try to set up. And we actually have 2 papers that start to build stochastic models for these that talk about sort of these deleveraging effects and stable and unstable regions. And these can actually anticipate the effects that we saw in Maker back in March. 2 further quick notes is that a lot of this can extend to wider DeFi settings, and we have some interesting conjectures there, so please check out the paper. And there are also some interesting design gaps that we discuss. And so that brings us to the end. Hopefully that motivates you to take a look at the paper. And so the papers are available on archive, and the latter 2 ones here are the price dynamic models I was mentioning. And lastly, I just wanted to mention that we're also organizing a DeFi workshop at FC. So please take a look at that and submit a paper if you're interested. Thanks. Are there any questions at this point?
Yeah, I think for questions, if you have a question, just feel free to jump in. I think we can do chaos. I think Surya, I see a hand raised, but I don't know if that's a typo.
No, it's actually a clap, like a clap emoji. That's not the hand raised.
Oh, okay.
Oh, thanks.
All right. Well, then, if I see no questions interrupting, then why don't we transition to our next speaker? Thank you, Ariah. I'm sorry I forgot to introduce you. Ariah is a PhD student at Cornell in applied math, by the way. So great. Our next speaker is Patrick McCorry, affiliated with PISA Research. Patrick is an IC3 alumni, and he has a startup, Any.Sender. Patrick, I see your screen. Are you ready to go? If you are talking, I cannot hear you, Patrick.
Patty, you're on mute.
You're muted, bro.
Patrick.
You unmuted for a second and then it went back.
Can see your face, but can't see your screen. Or sorry, can't hear you.
Patty, there you are. You just unmuted. Okay, there you go.
Oh my gosh. Okay. So let me just jump back my slides. Awesome. Everyone can hear me now and you can see me.
Yes, it's good now.
Awesome. So just before I begin this, so what I've basically been doing for the past year is building a product called Any.Sender that makes it easier for developers to send transactions to the network, because sending transactions to Ethereum is a pain in the ass. And it's what got announced last week was we got acquired by Infura, so it's now going to be called ITX and Infura Transactions, and I got a free T-shirt, so that's really exciting. So the basis of these slides are very rough because I only had like 4 or 5 hours to make them because of the work last week. But I sort of want to highlight some of our thought process around our relay and sort of how the fee market is going to evolve over the years, and even how it's already evolved. So this is basically another take on MEV. It might have some controversial ideas, and maybe you already knew some of this, but hopefully you enjoy it. So what is extractable value? And I sort of want to give a very simple definition for this. There's basically when a user sends a transaction to the network, another party can find a way to profit from that. Very simple extractable value. And there's 2 ways you extract value. One is an overt fee. I attach a fee to my transaction, and the block producer can extract value from that because I'm literally paying them to include my transaction in their block. And the other one is like a covert fee. The transaction doesn't really have an explicit fee or a fixed fee, but another party can still derive profit from my transaction. There's 2 different fee structures now when we consider extractable value. If we consider Bitcoin's precedent in history, for extractable value, there was only ever really over transaction fees. The miner's creating a block, there's the pending pool with a list of transactions, and really all the miner has to do is sort the list based on the fee paid and put it in their block. And that's how they maximize the value they can extract from the Bitcoin network. to secure the network and to take, profit and cover their mining costs. If you want to reorder transactions in this block in Bitcoin, there's little to no impact of that. If you reorder Bitcoin transactions, you're not going to get any more value from that. And that's because all Bitcoin can do is send value. There's some cases where a miner could extract value from an external service. So we see with Ethereum Classic, if you perform a block reorg attack, you could actually send 100K to an exchange, do some trading, and then take your 100K back by reorging the blockchain. But realistically speaking, for stuff like Bitcoin and maybe even Ethereum, that's a block reorganization attack's not really realistic at this point. So there's no real way to extract value other than Bitcoin. So this was never really a thing in Bitcoin, to be honest. It only really became a thing in Ethereum. And why is that? Why did extractable value become a thing in Ethereum? I think because there's two differences in my mind. One is that there's now online services with extractable value. We no longer have to rely on an external service and putting off some, funky block reorg attack to extract value. You can actually get it. There's actually services that sort of live on Ethereum, like, Uniswap, there's lovely little Unicorn and Balancer and other DeFi applications. And the user's transaction intent is slightly different. I'm no longer sending transactions just for value, but I actually want to send a set of transactions because I think I can make profit from that. So this is like a little diagram here, right? My first transaction, I put 5 ETH in. After I complete the set of transactions, I'm expecting to get 12 ETH. So that could be some arbitrage moment, for example. Maybe I short or long ETH, and then the next transaction, I'll profit from that. And that's sort of very different from the Bitcoin use case because now users have a very good reason to pay high fees on the network. But there is one issue with Ethereum, and that's the way transactions are signed. The user will sign a transaction thinking it's going to do A, but in reality it's going to do B when it gets mined on the blockchain. So one possibility that miners could do, and I think there's some evidence of this, maybe Phil can comment on it, they can take a list of transactions and they can actually place their own transaction in between. They can order the transactions in the block to maximize their own extractable value. One might be, getting transactions that flip the price one way, doing arbitrage, and then flipping it back to where it should be, as a very naive example. And that's because you can change how, the state of a contract, or you can change the outcome of another user's transaction. And so you can imagine here what the miner will do is they'll fetch all the transactions, and now it becomes this machine learning problem. They'll fill their blocks in different ways, and they'll look at how much they can extract value from this block. So in this example, they can extract 9 ETH, and the other one they can extract 10 ETH. Again, very naive, simple example. But just coming across that the problem's no longer, picking fees from high to low, but working out the total extractable value from the block. But this is a lot of work for miners to do in 14 seconds, and miners typically have a lot more problems than just trying to, do machine learning on the mempool and the pending transactions. So there's a way for miners to outsource this work and just derive their profit from the network fee market, from the fee market itself. And there's some evidence from this from the dark forest. There's these really cool blog posts about this malicious mempool. And at a high level, you could imagine that Andrew found this profit opportunity. He sends 3 different transactions, and he's going to make this 12 ETH. He sends the list, the set of pending transactions to Ethereum, and the bid's 1 ETH. That's how much that's the transaction fee he's associated for miners to pick up his transaction. Phil comes along. Phil's a bit naughty. He's a script kiddie. He can simply copy and paste the same set of transactions, but then sign it under his credentials. And now Phil's going to get the 12 ETH, but he's paying a higher he's paying a higher bid of 2 ETH. So the miner can say, well, I could take Andrew's transactions, but Phil's going to pay me more, so I'm just going to take his transactions. And this can keep going back and forth, and it becomes this gas auction within 12 to 14 seconds. Andrew places a bid, Phil places a bid, Andrew try to up him, Phil up him. And basically, in a very simplified world, these parties are willing to pay up the Y in the transaction fee, considering they're going to make Y in profit. It's not strictly that way because you'll have different strategies in how you'll maximize your gas auction. But that's quite interesting now because the fee market provides a proxy to the miner. The miner doesn't really have to do anything. They just let the market compete on these profitable transactions, and they just extract the value of that from the fee market. But of course,
beep.
Okay, beep. Awesome. I'm nearly done. Yeah, awesome. So this is only a single transaction gas auction. For single transactions is a bit boring overall. But now what we're starting to see are these layer 2 rollups and these shards that basically create blocks. They sequence blocks, and they're going to send them to Ethereum. And realistically speaking, what you can imagine is that these rollup providers become sequencers. Their job is to perform some machine learning on their block and work out the maximum extractable value, and then try to get their block into Ethereum. And so you can see 3 companies here. They're all bidding to try to get their rollup block in the main Ethereum blockchain. If they get their rollup block in, then obviously they extract value, and so does the miner. Rollup providers can extract Y value from all their users, and then propose a candidate block that again pays up the Y in the fee. So essentially, miners are going to outsource this machine learning problem to the open market, and all these sequencers may compete in that. And the way relayers fit into this, so this is what we were thinking with any sender, was that relayers will actually specialize just in competing in this fee market. You're going to have these large rollup providers who can spend a lot on fees. They don't want to pay up the Y. They want to maximize their profit. So a relayer will compete in that market and pay the best price at any time, basically trying to compete, not in like a full competitive gas auction, but just against other rollup blocks. So this is a good idea I've had for a while, and I'm trying to write up about it now. So if you have any thoughts or comments on it, I'm quite interested in that. And the final note is, when you think about extractable value, you may think it's some weird Phoenix exchange. There's always working against you and always trying to, take all your profits, then you don't make any money at all. But smart contracts can somewhat constrain the extractable value itself. So this is some code from Uniswap. Swap tokens for exact amount of tokens, and I can set plus 1 or minus 1% slippage.
Finish your sentence.
Yeah. So if there's my last sentence there. So as a user, as long as my transaction tolerates 1% slippage, they can extract the 1% value from me. They try to extract any more, then they'll invalidate my transaction. There's no point processing it. So now that actually adds to the machine learning problem of how they extract value within these constraints. And I think that's quite cool.
Thank you, Patrick. Our next speaker, will be Phil, who is a CS student at Cornell, advised by Ari Jules, and he'll be talking about miner extractable value, which is a related topic. So Phil, take it away.
You guys see my screen okay?
Yes.
All right, great. So great talk by Patrick, and we're going to be continuing this theme and talking about why everything in the world is miner extractable value or extractable value, and why you should care about this no matter what you're doing in the blockchain space. So the first thing I want to say is that blockchain money gives us many opportunities for progress. This is an upcoming paper that's going to be coming out that's joint work with Kushal Babel, Mahimna, Kelkar, and Ari Jules. And what we say in this paper is basically that unlike legal money, blockchain money has 3 properties that Patrick has called out, kind of 2 of them. It's composable, it's deterministic, and it's easily modeled. And surprisingly, this allows us to use MEV as a definition of actual contract security. So that's what I'm going to be talking about today. I'm going to be trying to prove to you that the holy grail of all smart contract security studies is MEV. And try to convince you that you should be working on MEV. So to see why, let's start with a contract intended to swap between 2 different assets, here ETH and US dollars. One way to instantiate such an exchange is what I call the monoswap method, kind of based on a real contract that you might have just heard Patrick talk about. And the way this works is you'll have a smart contract on the blockchain that holds 2 different assets in deposit, let's say here Ethereum and US dollars. And this smart contract will maintain that the product of its balances in each asset is the same number. So here, this product's going to be 1. So one example is, let's say you have 2 users who want to make transactions. Alice wants to sell 1 ETH, and Bob wants to buy 50 cents worth of ETH. Alice will send her ETH to the contract. She's now upset the balance in the contract. So the product of the balances is now 2, which is not 1 anymore. So to restore this invariant where the product is 1, the contract has to send Alice back 50 cents in USD. So Alice has essentially placed a market order to sell 1 ETH here and gotten a price of 50 cents per ETH. Bob does the same thing. He sends his $1.50. Now the contract has 2 ETH and 2 US dollars for a K of 4. So it has to send Bob back 1.5 ETH. Great. But what if instead Alice and Bob did the same transactions, but in reverse order? So doing the same math, Bob sends his 150. K is now 2.5. He has to get 0.6 ETH back. You should just trust my math on this. Alice sends her 1 ETH, and this time she's going to get back $1.80. So obviously there's a big difference here. On the left side, Bob is happier because he got 1.5 ETH for his USD instead of 0.6 ETH. And on the right side, Alice is the winner because she got 179 instead of 50 cents for her ETH. So who picks the difference between these two orders? I think you know the answer by now, given the last talk. And the answer is that the miners do. So this comes from a term called miner extractable value, which we defined in this paper called Flash Boys 2.0 here out of IC3 with quite a few contributors about 2 years ago. And we defined miner extractable value in that paper as a measure of how much cryptocurrency a malicious validator or miner can extract from a system by reordering, censoring, inserting new transactions, or otherwise behaving maliciously on the cryptocurrency network. More specifically, if you are kind of assisted by having more formal notation, this definition is something you can actually measure, and it's how much ETH a special miner account on the blockchain sorry, the account should be there. I keep forgetting to fix these. Can, given a set of user transactions T and an initial state S. So these transactions T are the transactions from other people the miner has seen on the network. It could be Uniswap trades, could be any other kinds of transactions. The initial state S is kind of the state of the world before the miner started playing their game. And the set of contracts C is kind of the set of code that the miner knows about and can deploy and use in its game to kind of try to extract more value from other people. And the options it has here include inserting its own transactions, censoring transactions out of T, and reordering transactions in T. So what we claim in basically this upcoming work is that MEV kind of represents this new frontier where it sort of unifies all these other problems that people have been studying throughout computer science and economics related to trading systems and related to smart contracts. One of them being arbitrage, and this is kind of why we named the original paper Flash Boys, because it has to do with bots that are interacting with programmatic financial systems and trying to extract as much money for the people who are running the bots as possible. Another thing you've heard about in the first talk today was exploitation. So people who take advantage of unexpected patterns in systems to gain more money than other people expect them to out of these systems, for example, in stablecoins. These could be, for instance, the analogs of black hat hackers in this new kind of financial sphere. Software verification, so things like securing spaceships and how do you build secure software. MEV, and this plays into consensus and miner security. Like Patrick said, it affects the stability of the miner games that are being played on the blockchain. And also composability. How do we reason about all these DeFi Legos that are interacting together? So these are all really the same problem. And I'm going to explain to you a little bit more about why. So remember our definition of MEV. And let's talk a little bit about composability. So let's say you have Alice and Bob who want to do their trades here on Monoswap. What is the MEV in this scenario? Well, the MEV that a miner can steal, let's say they have a perfect attack. They can at most take, let's say, the 1 ETH that Alice has, the 150 Bob wants to trade, plus all the money in the contract. So that's at most $2 plus and 50 cents plus 2 ETH worth of MEV on this side. Now let's say you have users, Carol and Dave, who want to place a bet on the future price of ETH. And the way they do this is they write a contract that looks at the Monoswap contract and looks at the ratio of these assets, which is a proxy for the price kind of being offered on the market by this contract. And Carol, who thinks ETH is worth a little bit, will win this bet if the Monoswap contract ends up having more ETH than USD. Otherwise, Dave will win this bet. And let's say they each bet 1,000 ETH on this outcome of this contract. Well, now the miner can extract at most the sum of these bets, so the 2,000 ETH, plus all the original MEV they could extract by reordering Uniswap, which is strictly more. So the point here is that things that other people do on chain and things that other people deploy using your contract affect the security of your contract and affect how miners will interact with it and affect the guarantees that users like Alice and Bob will get in your system, and cause way more incentives for miners to actually take this value and exploit the system. So in this framework, we actually define composability as basically if a new contract C prime does not introduce more MEV to the system after being deployed than was there before, we consider C prime to compose with all of the sets of contracts that were developed before. And we encourage anyone who's developing financial instruments or smart contracts to reason about how their instruments compose with other things that are deployed on chain or other things that could be deployed on chain in the future. So in our upcoming paper, we're going to provide a suite of modeling tools that look like this, that basically provide really simple techniques to model contracts like Uniswap in a purely abstract mathematical way, just saying what's going to happen to sort of each user's balance as a result of abstract transaction flows. That's going to allow us to do things like prove things about Uniswap. So here we prove that if you have 2 versions of Uniswap deployed that are trading the same assets. Sorry?
2-minute warning.
Cool. Yeah. So if you have two contracts deployed trading the same assets, there's always going to be some like instability there where MEV is going to be exposed no matter how users trade, unless they trade identically. We also provide a formal model that's executable. So we use something called the K framework to mathematically define this. Again, this is all defined in terms of abstract mathematical logical operations. And that allows us to derive executable models, things that we can actually run on a computer. So we can take logs of all the transactions that have ever happened on the blockchain, just spidered from BigQuery or other blockchain sources, and we can run them through our executable models, and also ask the computer to prove things about these transactions. So we can prove things about the MEV. We can say, like, prove to me that no matter how the miner reorders this and what transaction they do, the MEV will be between these bounds. And because our software framework is kind of mathematically defined and it knows how to make queries to mathematical solvers on the back end, it can start to answer these questions about what does MEV look like when various contracts interact, what are the best strategies for bots, and also how do we design secure contracts. So why do we use K? Well, because K already provides this modular technique where you can have a single formal mathematical definition that generates all these different tools. And each one of these tools is useful in DeFi, either to debug the models we build, to find optimal strategies for bots, or to monitor the security of the chain in real time. So what we're trying to develop in this work is this set of open source and human readable models for DeFi code. There's also some existing K models for various contracts that kind of can interface with this in various ways. Anyway, we actually built this, we ran it, it works. Here's the log of how long it takes to validate our model. We validated this against every single on-chain Uniswap and MakerDAO transaction. And we used it to find MEV up to 200 ETH in Uniswap v1, Uniswap v2, SushiSwap, as well as in the composition of MakerDAO composed with Uniswap using MakerDAO as an oracle, kind of showing that our tool can reason about these abstraction boundaries in these compositions. The last thing I want to say is that we're also starting an organization to front run the MEV crisis. So you can read about this on the IC3 website. If you're interested in MEV research, you should get in touch. And you should also come to our panel, which is going to have a heavy audience participation component with questions about this talk or other forms of discussion. I really can't wait to talk about why MEV is part of the broken fee market. All right, that's it. Thanks, guys.
Thank you, Phil. Our next speaker is Mahimna Kelkar, who is also a PhD student in CS, advised by Ari Jules, who will be talking about order fairness. I can see your screen, Mahimna. Go ahead, take it away. I will give you, I'm going to stop saying beep and I'm going to say 2-minute warning instead for clarity. So take it away.
Sounds good. All right. Thank you, Tyler. As Tyler said, I'm a PhD student at Cornell University. And today I want to talk to you about order fairness for blockchains. So we've seen DeFi sort of have a big boom in the last few years. And today, DeFi accounts for over $13 to $14 billion in market cap. We've seen DeFi instruments like decentralized exchanges and lending contracts and financial derivatives. So clearly DeFi is pretty hype right now. But what the community has noticed recently is a lot of these DeFi instruments suffer from transaction reordering attacks. And following Phil's paper on flash bots, we've noticed front running and back running and transaction insertion attacks and MEV style attacks. And current permission and permissionless protocols don't really have any way to account for any fair ordering properties. So for example, in something like Ethereum, the miner has complete control over what kind of ordering it wants to choose for the block. So some of the current techniques that we've seen for any sort of ordering, we have something like censorship resistance, but here any form of reordering and insertion is still possible. We've had in the permission setting, electing leaders randomly who get to choose the ordering for that block. But adversarial leaders will eventually get elected and they can still order as unfairly as they want. We've had some other techniques like hiding transaction data through threshold encryption or come in and reveal schemes. But here, any form of blind reordering is possible, or manipulation via metadata or IP address or colluding with the users. So blind reordering is problematic because we could have instances where you want to get first through the door or last through the door, and you don't really care about the actual content of the transaction. There's other techniques like choosing a random transaction ordering. But even this is not fair, as I'll claim, because you can create new transactions and just flood the network and have a very high probability of your transaction being selected first. So we started this work with co-authors at Cornell. This was a paper published at Crypto 2020, where we defined this notion of block order fairness. So basically, the informal definition is as follows. If a large fraction of nodes are input M1 before M2, where M1 and M2 are transactions, then all of the honest nodes will output M1 no later than M2. So we choose no later than instead of before because there's an impossibility result associated with the other definition. But I will say that this definition is minimally relaxive in the sense that our protocols will achieve the stronger definition whenever there's no impossibility result or contradiction. In terms of random versus fair ordering, I'd like to highlight that even like a random ordering protocol, you can have an adversarial transaction being ordered before an honest user which arrived first with like a 50% chance. And if you start to flood the network with a lot of these adversarial transactions, you'll have a much higher chance to get your transaction sequence first. And on the other hand, a fair ordering protocol guarantees that an honest transaction which arrived earlier is the one that's actually sequenced earlier, regardless of adversary. So I'll very briefly talk about some of our fair ordering protocols. So we started with Equitas, which was a fair ordering protocol in the permission setting. This was from our crypto paper. So informally, Equitas takes place in 3 stages. We have a gossip stage, we have an agreement stage, and a finalization stage. And each of the transactions that's input into the system goes through these 3 stages before eventually being output. So in the gossip stage, you might have guessed that transactions are gossiped throughout the network in the order that they're received by each of the individual nodes. And the agreement stage, nodes agree on which orderings to use for finalizing the transaction. And the finalization stage is a completely leaderless local algorithm that can take these ordering lists and output a fair transaction ordering. So our paper showed that because these broadcast and agreement primitives can be realized from any consensus protocol, we actually provide a general compiler that can take any consensus protocol and transform it into one that also provides order fairness. And in a follow-up paper, we introduced this player replaceability lemma that allows us to transform the same problem into a permissionless setting. So this player replaceability lemma allowed us to continue transaction orderings from other nodes and use proof of work mining or proof of stake mining for this continuation. And now you can sort of reduce the permissionless problem to the permission setting by creating modular chains that correspond to virtual parties in a permission setting. So we can have K modular chains in the permissionless protocol, which intuitively correspond to K virtual parties in a permission setting. And now we can use our finalization protocol from before to construct the fair final ordering from these K virtual parties. So as a simple example, we can have a single chain protocol where you're mining proof of work blocks, where let's say the logical continuation of your proof of work blocks is 3 blocks behind. So you have 3 modular chains here, the blue one, the green one, and the red one. But your proof of work continuation is just mined on top of the previous block. So you end up with 3 modular chains, as I said before, and then you can use the similar Equitas finalization to construct the fair ordering protocol. We can also construct a parallel chain protocol where we mine these chains differently and simultaneously. So instead of mining one chain with all these modular chains inside of it, we can mine the 3 modular chains simultaneously. And then similarly use our Equitas techniques from the permission protocol to create a fair final ordering. So that's some of the protocols that we developed in our first two papers. And we think that this is just the first step of the research, and it did good work in laying a solid foundation for the study of order fairness. So I'd like to talk to you about some next steps and where I think that order fairness will go. And I think this is particularly interesting for our industry partners because some of the things that I will talk about will be much more scalable and potentially better than our first few constructions, which were more so in the theoretical realm. So a couple of research directions that I'm really excited about are fast order fairness.
2-minute warning.
How exactly do we have a fast protocol that does order fairness? And what kind of definition is good enough for order fairness? So we can have a much weaker definition that doesn't really account for much of the transaction reordering problems that we saw and have a scalable protocol. Or we have these really strong, powerful order fairness definitions where the protocols end up being very slow. So can we find some middle ground where we have a good enough definition for fairness and also a scalable protocol? The second major research goal is sort of in line with the first one in terms of scalability. So Ethereum, for example, has seen the community move out of the main consensus layer and think about scalability in terms of sharding or layer 2 protocols like rollups. So the question is, how does this interface with fair ordering? For example, you could think about rollups having more power to the person creating the rollup, and does this inherently deteriorate ordering problems? And the third problem is, how does order fairness interplay with transaction fees and the fee market and gas auctions and all of the MEV stuff that Phil talked about? All right, cool. So I've just left my email address as well as a link to my website in case you want to reach out, and I hope you enjoy the presentation.
Okay, Mahimna, thank you. We have 30 seconds. Are there any questions before we run on to the next speaker? I really cannot tell if those are clapping or questions. Okay, I'm going to assume that's a no. I'm going to introduce our next speaker then. Our next speaker is Sergey Nazarov from Chainlink. He's going to talk to us about oracles. Sergey, are you on the line?
Can you hear me?
Sure can.
Great to chat with all of you. Thanks for including me in the talks here, and it's always a pleasure to be with everyone here at IC3. I'm a huge fan of everyone here. So I'm just going to jump into the presentation. Then let me share my screen very quickly.
Just a reminder, I will give you a 2-minute warning prior to the end of the talk.
Great, thank you. Can you see my screen okay?
Yes.
Actually, 1 second, I have to turn off a whole bunch of things. Okay, here we go. Okay, cool. Sounds like we're good. Cool. Hi, everybody. Good to chat with you again. So we're going to be discussing the importance of oracles, specifically as they relate to DeFi. Just as a quick refresher, oracles are necessary because blockchains, while they're great as smart contract state machines and data structures to store tamper-proof pieces of data, they can't actually access external data sets, and they can't access APIs, and this limits them. The way it's limited them thus far is that it's made them about tokenization. So far we've seen blockchains basically be about, let's make tokens. That's been good. It's seeded a lot of value into the ecosystem, made the ecosystem graduate to something useful. I kind of see tokens like the email of blockchains. Now I think we're transitioning to a world where things are going to be based on events. That's because the majority of contracts out there in the real world are in fact based on events. And so I think the shift that we're now starting to see is from a world where people are building contracts around tokens to a world where people are building contracts around events. The way that contracts are built in the real world, in the financial sector, in the trade finance sector, in the insurance sector, and so on. This is strongly evidenced by the fact that decentralized finance is rapidly growing, and the rapid growth of decentralized finance basically leads us to believe that this is the next frontier of how smart contracts and blockchains are utilized. That while we might have started making tokens and using private keys to vote and using tokens to vote in DAO structures, that was kind of the tip of the iceberg and the beginning of this technology being used for certain types of contracts. Whereas the evolution into various financial products in the form of DeFi is actually the more complicated, more advanced, more expansive variant of what smart contracts can do, which is underpinned by the value seeded through tokens and made usable through the security of private keys. But still, that, in my opinion, is the future, and that future is just getting started. if you look at what DeFi contracts actually are, they are really a combination of two things. They're a combination of on-chain smart contract code, which basically makes a tamper-proof, immutable state machine that everybody can rely on as a single record of truth across organizations, and something that reliably stores value and reliably moves and transacts value in ways that centralized systems simply can't create transparency. They simply can't create the same security. They simply can't create the same ownership dynamics via private keys, whereas a smart contract state can. And making that scriptable is something that Ethereum did very well and is now being expanded to various other chains. The other piece of it is, how do we actually interface that state machine with the external world? How do we connect it to market data, weather data, the commands from other systems, payment systems that aren't on a blockchain? And that's really the next set of problems around how do we get smart contracts into the world of real world useful use cases. Now, the way that this is approached from our point of view is to the creation of an oracle. An oracle essentially takes data from the outside world, whether that's market data or payments data or weather data or even commands from other systems, and shuttles that data into blockchains while actually observing what's going on in a contract and informing the system in the traditional world. Now, we don't have enough time to go into all the nuances of what makes an oracle. We're probably going to spend more time on looking at, what are the research problems and security issues that we as a group of people would like to think about and hopefully solve. But fundamentally, I think what's useful is to think about what makes up a good oracle. And it begins with being able to select good sources of data and being to compose those sources of data into a logical, manipulation-resistant format. It continues to being able to prove the origin of data and to prove that data actually originated at a certain specific server from a specific data provider. You need something called data validation, which is where consensus comes in, and you're able to validate and aggregate values and prove that the state of the world is actually represented by a collection of data sources and a collection of values from multiple sources. You then need to guarantee that those aggregations and that final kind of aggregated value will get into a contract, which is where crypto-economic guarantees come in. And just like blockchains have incentives to guarantee data is provided in the form of transactions, we have a crypto-economic system to guarantee that data is provided. That system's been working pretty well through high gas prices, through sudden hard forks, through various other infrastructure outages. Our system of crypto-economic guarantees has remained up and providing data to contracts that secure anywhere between 2 to 5 billion in value. So that's the crypto-economic system is an important consideration. And then finally, in more advanced use cases, you arrive at data privacy concerns, which is where Deco and Towncrier and other systems come in, where you can prove that not only did data come from a certain source, but you can allow the data to retain its privacy, which opens up a new world of data that is going to be necessary for certain use cases. All of these things we kind of work on in production today. We already basically trigger anywhere from 2 to 5 billion in value, depending on the day, with much more in different stages of integration. We provide market data for DeFi. We're the most widely used market data kind of oracle mechanism out there right now. We provide gaming data for various top gaming smart contracts. We provide weather data for insurance contracts. We provide proof of reserve to show that an asset is actually locked up somewhere. And we provide various other data like election results to prediction markets and various other use cases. So the problems I'm going to be talking through with you here are actually born out of real world application, real world experience, real world usage, and real world dynamics that in some cases we've seen people deviate from certain dynamics that we recommend, and that has led to failure. And in other cases, we see people adopt them and that lead to certain levels of security. So I think it's useful for us as a community, as a research community, to think about what are the problems that people are running into. And there are obviously the near-term problems, the medium-term problems, and the long-term problems that aren't happening yet. I'm going to begin with the near term and go on to the medium term, and then possibly go on to what some of the long-term considerations are if I have time. In the near term, people are essentially improperly trying to compose their own oracles. They're trying to say, I can select 2 or 3 exchanges. They all look good. Exchange A, B, and C has enough volume. I seem secure. But then guess what? Volume shifts. And because they didn't build a monitoring infrastructure, they just architected a system that fundamentally can't keep up with where price discovery happens. they now are getting data from what are called thinly traded markets, which are very easily dislocated. So what that means is that you can essentially manipulate those markets for a very low cost. I think we've seen well over 100 million compromised, probably well over 200 million, depending on how you count the different exploits, compromised because of this simple design decision and flaw. This design decision is not one that we made. We completely avoided this issue. None of our users were ever exposed to this. But one category of risk is how do people compose data sources? And unfortunately, certain people have decided to compose them in ways that have exposed them to risk, leading from anywhere from exploits of anywhere from 1 million to 90 million to various other amounts. Generally speaking, I think the most egregious form of this exploit is when people just use one exchange. They basically say, I'm going to ignore the possibility of people manipulating a single trading venue, and it's going to allow them to be exposed to that risk. And it's a very serious risk, and it's one that I think that, merits various kind of research, merits various kinds of mitigations like the system we have. The nuance here is that some people actually think that if they get 2 or 3 other exchanges beyond the one exchange, they'll be secure. Unfortunately for them, that's a very inaccurate assumption that's going to simply lead to more loss. And the manipulation of these prices is kind of simple in that you simply need to manipulate an order book. So this is the first string of attacks that you've seen. They've come from this. They've come from the ability of people to manipulate a single exchange, or in the more advanced use cases, we're now seeing to manipulate 1 or 2 exchanges because the people making a DeFi protocol have unfortunately composed an Oracle system out of 1 or 2 data sources only. The way we approach this is we source data from hundreds of exchanges with multiple data providers so that we get something called market coverage. This is our approach. We're always thrilled to hear feedback on it. But fundamentally speaking, this is how we've so far solved this problem, and our users have went unexposed to these exploits. The second medium-term set of concerns that I have about even this category of exploits is that people seem to want to push data methodologies that don't work. They seem to want to say, in times of volatility, something like time-weighted average price can work. In times of volatility, something like time-weighted average price can't work, quite simply because it won't reflect the accurate price, which is why the vast majority of the real world financial industry uses volume-weighted average price, and almost nobody uses any time-weighted average price methodologies whatsoever.
Finish your thought.
Yes?
You're out of time, so just finish your thought, and we'll go to the Q&A section.
Sure. So this is a medium-term concern, and how to get people away from relying on poorly formatted kind of measures of defining price. There's another serious concern where people want to combine low quality data with higher quality data. That's an obviously bad idea that research should reflect, and research on these various systems should come to reflect. The long-term concern, the long-term dynamic that I actually see that's also worth researching and thinking about how to architect systems is people moving from monolithic designs to microservices and service-oriented architectures. What I really see is that the DAO, is that service-oriented architectures provide separation of concerns, reusability of services, and security. And if you were to really think about it from a research point of view, the DAO was kind of a monolithic contract that took a lot of security risk on and didn't separate concerns. And what you see now in DeFi is composable DeFi contracts that do separate concerns. So as a researcher, if you guys are making this, I would really seriously think about, how do I suggest or design separate services that can separate out the different risks? And that's already the design pattern that we see in DeFi. And that means the composition of oracles together with various smart contracts that are small in their, separation of concerns in their sphere of responsibilities, but are therefore secure.
Okay, Sergey.
Sorry, just one last thing really quickly. All of this we're really thrilled to discuss with you. We're actually now in the process of launching a new exciting initiative called the Smart Contract Research Forum. It's a forum that's meant to bring the industry participants and the academics together. It's meant to provide industry feedback on new research, enable the adoption of existing and new research, and it'll have a growing research grants program. It's something that's only getting kind of really announced here and launched just now. We're opening up to the IC3 community and to everybody that wants to think about all these problems together with us. whether those problems are around consensus, oracles, governance, various cryptography, secure systems design. It's a place that is supposed to be kind of well moderated and impartial and focused on providing the research community with a place to connect on industry participants, connect with industry participants on all of these issues, which we find to be quite important. And so we're excited to work with you and find a good way to work in the Smart Contract Research Forum on all of these issues. Thank you. Sorry for going over.
Yeah, no. Okay, so now we're going to go to our question and answer session in gather.town.